Hi, everybody. Welcome to the FORCE seminar. Thanks for joining us today. I'm Kara Brugman, research scientist and outreach coordinator for FORCE.
And I'm Kyusei Tsuno. I'm also a research scientist.
And today we have with us Tim Officer from GSE CARS at University of Chicago and Argonne National Laboratory to talk about simulating subduction zone slabs in the lab. Before we begin, I do want to remind everybody that this meeting is being recorded. It'll be available on YouTube next week. And if you'd like to follow us, we're on Twitter, LinkedIn, Instagram, and you can join our mailing list at force.asu.edu/newsletter to get all of our updates. I also want to remind you that we're holding our first winter workshop this January. Registration will probably be open next week, and we do have some opportunities for travel funding for students, so keep an eye out on your email for that announcement. We have one more seminar this semester with Dr. Jin Zhang from Texas A&M University. She'll be speaking on November 3rd in just 2 weeks about the possibility or not of plate tectonics on Mars. And I wanted to give everyone just a brief construction update. So Ichiban is completed. We have a picture here of a lot of the team who are involved in the training installation. We did training at the beginning of the month, and you can see a picture there of our PI, Kurt Weber, signing the final inspection report, officially turning Ichiban over to us. The Sumitomo said it was Ichiban's birthday. So that was really exciting. Currently, the catwalk is being built around Ichiban. And next in November, the team from Riken will come out to commission our high pressure torsion press. So without further ado, I'll turn it over to Kyusei.
All right, so thank you, Tim, for giving a talk in the FORCE seminar. And Tim obtained a PhD from the University of Western Ontario in Canada, working with Professor Rick Secco, and worked on understanding the deformation mechanism based on a multi-anvil experiment with acoustic emission techniques. And now he's working at the GSE CARS, working with Dr. Yanbin Wang. And part of his research, which I know from his paper, is his work is for understanding deformation using D-diapress with acoustic emission technique. So today he will be talking about high pressure temperature deformation experiments using several earth-forming materials and see how phase transformation can affect the catastrophic failure under nominally ductile condition. So Tim, time is yours.
So the slab in the lab is my catchy title. And I'm going to be talking about simulating deep focus earthquakes through transformational faulting in some olivine analogues. So just a brief background on fracture mechanics. So on the left here, and you can see my mouse, right? Somebody, Joanne, can you? Yeah. Okay, so on the left, you see this rock here, and you're compressing it in 3 directions with the maximum compressive stress in the vertical direction, and then equal compressive stress on the sides. And then you also have shear stress. So shear is the stress that is in this direction where you have a force, but the stress is acting parallel to a slip plane, and you have the maximum shear stress along some diagonal here. So imagine you take this rock and you start to compress it, or you start to stress it in the sigma 1 direction. Well, what's going to happen is it's going to start getting shorter. It's going to strain, and then eventually, so the axial strain is increasing, you start to generate these microscopic cracks. And then as times go, these cracks start to get bigger, because what happens is you have maximum stresses right at the edge of the cracks, so they start to grow and elongate, and eventually they'll start to interact with one another, and they call this crack coalescence. And then you can start to have a shear band forming, and eventually the rock will break, at least at low pressure. So this is just an example of that. So here is brittle behavior at the top. You increase the differential stress until it just fractures. But then as you increase pressure, you start to get shear bands forming and more ductile flow. So eventually you transition from ductile behavior, or from brittle behavior, sorry, to ductile behavior. So here's some real data in the top right here. At 0 MPa, you increase the stress, and then eventually it just breaks. You lose all the stress. 10 MPa, same thing. 50 MPa, you have this sort of brittle ductile transition behavior, but eventually the rocks just become ductile. So as you increase pressure, it becomes harder and harder to generate cracks. So then rocks will just start to flow. And if you look at these, so you have some real rocks on the bottom here, and at 28 MPa, you get brittle fracture. At 40 MPa, you get ductile flow, but you can sort of see a shear band forming here. But by 100 MPa, you just have purely distributed ductile flow. So as you increase pressure, it becomes harder and harder to fracture rocks. Now, in addition to that, when we think about the Earth, as we go deeper in the Earth, we increase the pressure, so it's harder to break rocks, but we also increase the temperature. So this is just an equation showing the shear stress required to have ductile flow, and it's proportional to an exponent to 1 over t. So as t goes up, the stress goes down. So if you look at the strength of rocks as a function of depth, they get stronger and stronger and stronger as you're increasing pressure, but eventually you reach this ductile transition, and then they start to lose strength and have ductile flow. And here on the right, it just shows the actual depth. So if we're going down along the geotherm, and somewhere around sort of between 50 and 70 kilometers, we transition from brittle behavior into ductile behavior. So based on what we know about rock mechanics and rheology, we wouldn't expect earthquakes to occur below about 70 kilometers. Nevertheless, if you look on the left here, this is the number of earthquakes as a function of depth. So most earthquakes are shallow, and that's not all plotted here. But then below 70 kilometers, they don't stop. They keep going. You see this sort of exponential decay. And then down here below 400 kilometers, you actually see an increase in the rate of seismicity. And these deep earthquakes, they happen in subduction zones. So the slab is much colder than the surrounding material. And so you have cool rocks on the inside that are fracturing for some reason other than ordinary brittle fracture, which we see for shallow earthquakes. So there's basically so the differences versus shallow and deep earthquakes, well, obviously their focal depth. They must operate by a different mechanism because you can't have brittle fracture at these deep conditions. And deep earthquakes have far, far fewer aftershocks, sometimes none, even for a magnitude 8 earthquake, where a shallow earthquake would probably have hundreds. And then the similarities are basically everything else. They have the same focal mechanism, sizes, B values, stress drops, et cetera, et cetera. So there must be something different about the rupture mechanism, yet when they rupture, they seem to behave very similar to shallow earthquakes. So there's basically 3 competing hypotheses of how these earthquakes occur. One is a thermal shear instability. So basically, you're straining the rock, it heats up frictionally, which softens the material, which leads to more strain, which leads to more heating, and you end up with a runaway, which is what they're trying to show in this sort of simulation at the bottom here, and the red is melting. So eventually you get a melt band to form, and you can slip along that. The other is dehydration reactions. So as the slab descends, you start to go through transformations where minerals will dehydrate, and people have speculated that this is somehow related to the seismicity down there. And I'm not going to explain this complicated plot, but what these people found is that when they dehydrated rocks under high pressure, they would fracture and they would generate acoustic emissions. But what I will talk about for the rest of this talk is you see as you go below 400 kilometers, you actually see this increase in seismicity. And people have long speculated that this is somehow related to the transformations that happen in olivine at these depths in the transition zone. So the slab is much cooler than the surrounding. So now you have in the core of the slab, you have cool material that can persist metastably until deeper depths because you need temperature to get the reaction to occur. So you can have metastable olivine. that goes down very deep, and then somehow this transformation is thought to lead to earthquakes. This is just the global distribution of earthquakes, deep earthquakes. The deep focus are in red. You see some in South America, particularly a lot in Tonga, as well as up around Russia. But the point of this slide is just to show that if you look on the right here, these are the number of earthquakes as a function of depth. And you just see that there's a lot in Tonga, but in Japan, they seem to stop around 600. On the South America ones, they have a total absence of seismicity between about 300 and 600, but then these jumps. So depending on which subduction zone you look at, the seismicity can vary pretty dramatically. Now, it would be very nice to test this hypothesis, like let's take some olivine and transform it and get it to break. But it's very difficult in a deformation apparatus to reach the pressures and the temperatures are easy, but to reach the pressures required to transform olivine to Wesleyites or ringwoodite. So what people have done is they take analog materials. So Mg2GeO4, you replace the silicon with germanium. This lowers the pressure required to transform in the phase boundary. So now you can run an experiment at around 3 GPa and generate the transformation. And back in the late 80s, early 90s, Harry Green and Pamela Burnley did just that. They took some Mg2GeO4 and then they deformed it and heated it up. And what they found is if it remained metastable and they didn't generate the transformation, the mineral would be ductile. If they heated it up a lot and they generated a lot of transformation, it would be ductile. But there was a sort of temperature sweet spot in the middle where if they just generated a little bit of spinel, it would be enough to cause the mineral to break. Now, they came up with a theory where, so in the ordinary brittle failure that I talked about before, you're generating these tensile cracks, you're opening up these cracks that have stress concentrations at the end and they grow. And what they found, if you look on the right, this is spinel here in these lens-shaped kind of morphology. And they said, well, these lenses act similar to these tensile cracks, but instead you have a reduction in volume, and then you have an anti-crack. So it moves inwards, but stress concentrations at the edge cause the spinel to grow outwards. So you have a similar situation as ordinary brittle failure, where these anti-cracks take the place of tensile cracks. And here's just some pictures of some anti-cracks. Later on, Harry Green did this first, and then Alex Shubnall, and then this is a picture from Yanbin Wang's paper, and then this is an image that I saw. They found that these bands of spinel, so if you can see these sort of lighter bands here, which are pointed at by the red arrows, you have spinel growing in these long, thin, planar bands. And I should mention too, the idea was that the anti-cracks and these bands, the spinel is nano grain, so the grain size is so small that it can't support shear stress, and that's why they act similar to cracks or to shear planes. And you can notice too, these white grains that are kind of glowing, these are like germinate pyroxene, and you can see that when these bands pass through them, they actually shear the grain. So you have shear localization happening on these bands, and you can see this here. And then here you see a long band, which is in red, and it's shearing this grain, and then possibly shearing this one as well, these blue arrows. So we run similar types of experiments. So basically you have a pressure cell at the center, you have 6 anvils surrounding it, and at the center of your pressure cell, you have a sample, and typically about 3 millimeters long, 2 millimeters wide. Here's one of them. I'm assuming you can't see that. That's kind of the point. They're very small. And the anvils will then compress the pressure cell to bring it up to high pressure and bring the sample up to high pressure. But a key point, this is in the D-dia apparatus, where the top and bottom anvils can move independently from the surrounding. So once you're under pressure, you could advance these 2 anvils and deform the sample. We also have a synchrotron beam. So you have a monochromatic beam in which you can collect radiographs and X-ray diffraction patterns, which I'll talk about in a second, to measure stress and strain. And we also, on the back of the anvils, have piezoelectric transducers, which convert mechanical vibrations into voltages. So then we can measure any acoustic signals that are generated in the sample with these piezoelectric transducers. And this is just showing an example of an acoustic emission. So to measure the strain, we use radiography. So radiography is basically like if you have an X-ray, if you go to, you break your hand or something, or in this case, this dog ate a small car, and there's differential absorption between the car and the dog's bones, so you can see through it. By the way, the dog is fine. They were able to remove the car, and it's okay. But in our experiments here, you have the sample is gray. You have platinum foils so that you can see the edge of the sample. So you're measuring the length of the sample and seeing how the length changes. And then you have alumina pistons on the side here. And then as you're deforming the sample, it gets smaller in this direction because you're pushing on it. So we can measure the strain. Oops. We can also, with X-ray diffraction, we can measure the pressure and the deviatoric stress that we get in our, oh, I should have deleted this. But basically, so we're collecting full diffraction rings. Under hydrostatic conditions, these rings will just be circles, but as you generate some deviatoric stress, they will start to become ellipses. And this is just showing if we plot the radius, which is 2 theta, versus the azimuth, so it's like we're unwrapping these things. If it was hydrostatic, these would just be straight lines, but they become these sort of sine squared things. And then we can plot this and we can measure the deviatoric stress and the pressure. We can also get, if we integrate around these rings, just get a regular diffraction pattern. So here's an example of a typical MG2 GeO4 experiment. This is one that I ran, but Alex Shubnall was the first to do this in 2013. So I don't want to say that this is the first time this has ever happened. But basically what we're doing is we bring it up to pressure. So we're at about 3.2 GPa. And then we've heated it up to 400 degrees Celsius. And so the temperature is shown in orange here. And then the strain, at this point, it's unstrained. We haven't started deforming it yet. But then we start deforming it and the strain starts to increase at 400 degrees Celsius. And you can see that the amount of stress on the sample is also increasing the differential stress. So, but what you don't see here is any acoustic emissions because the temperature is too low. We haven't initiated the transformation. We're up here. This phase diagram doesn't go that far, but we're up here on this phase diagram, and we just have metastable olivine, no transformation, no acoustic activity. But then once we reach about 10% strain, so we're building up some elastic strain in the sample. And then once we've done that, then we increase the temperature, we initiate the transformation, and then all of a sudden you see over 1,000 acoustic emissions. So the sample just starts to break once you initiate the phase transformation. If you look at the end of the experiment here, so the last maybe sort of 15 minutes, if you look closely, what you see is you'll build up a bunch of acoustic events, and then all of a sudden you'll have a huge event like this that just completely saturates the entire trace. So you have this big jump, and then nothing happens for about 2 minutes. Usually you're getting acoustic signals every sort of 3 seconds on average. Nothing happens in this period. Then you start to have some more acoustic events, and then you get another one of these huge events where you generate a fault in the sample, and then nothing happens, few events, and this will happen sort of a few times towards the end of the experiment. We can also locate them, so we just look at the differential arrival times of the P waves, and we can invert for their locations, which is shown here. You can see that these are in the sample, so it's nice. It's not just spurious noise coming from anywhere. But what we really want to know is we want to know how certain events are related to particular faults in the sample. How do these small fractures interact so that we can lead to macroscopic faulting. So here, this is just some random events that I picked. Yeah, basically at random. So they look like acoustic signals. That's good. But if you look very closely, you'll notice that these two, they look very similar to one another. The other ones are all different, but these two kind of look the same. So what you can do is you can take the waveforms and cross-correlate them, because if you have the same type of waveform on a seismogram, that means that you had the same process created at roughly the same place within the sample. So the cross-correlating is basically, imagine my hands are two functions. You just bring them through one another until they overlap. And if they're very similar when you overlap, you'll set some sort of threshold and say, I'm going to call these ones alike one another. And that's just showing here. As this moves through, there was high correlation. Now there's anti-correlation. As soon as this gets over here, you get a nice overlap. And this is just an example of some events. This was from a group. There was about 240 of them that looked like this, but it's just showing that they're kind of the same. So from that, we can build up groups of events. And this thing here is called a correlation matrix. So imagine you take, this is event 1, event 2, event 3, and the same thing going down. And this is saying, well, event 1, and then it's showing the correlation value, which is goes from 0 to 1, from no correlation to perfect correlation. So you cross-correlate event 1 with event 1. Well, that's just 1 because it's the same event. 1 with event 2, you'll get some other value. 1 with event 3, some other value, and so on and so forth. Now, if you go down here, you're going to get the same values, because then it's just 1 with 2 and 3. So this is a symmetric matrix, and the diagonal is always autocorrelation, so correlation with itself. But if you do that for all, I think there was 1,500 events or so in this particular experiment, and then you find out which ones correlate together, and then you make them into a group, you can see that there's two big groups. This one has about 240 events in it, and this one has about 200. And then the rest of it is basically uncorrelated. There's a couple small ones with about 10 that are very highly correlated, but the overall seismicity is just random. But there's these two large groups that are very similar. So it's the same process that is generating the waveforms in these two categories here. So once you have these groups, you can assume that they're coming from the same process, and that they're probably coming from an area that's very close to one another. So the traditional method, the acoustics, or the locations I showed before, basically you just have, there's an event, it'll be at a different distance from different transducers, so it'll arrive at different times. You invert for the arrival times, and you can find out where it is. But you need a good velocity model to do that. Like maybe it's going to refract at these boundaries. All sorts of stuff is going to happen as it travels from the source to the receiver that you don't really know how to account for that. However, if you take two correlated events where it was the same process that created them, they're close to one another, now they take almost the same amount of time to travel to a single transducer. So, and they travel along the same path. So any weird stuff that happens to this acoustic signal as it travels will also happen to this one. So then all you consider is the difference in travel time between these two events. So this is called the double difference method. So instead of just looking at the difference of arrival times, you're looking at the difference in travel time between particular events. And if you do that, you can get very accurate relative locations, because you're removing any of the effects of the transmitting medium and the sensor response. So this is just showing the double difference method results versus the sort of traditional method. So the double difference ones are in their solid colors, and then the other ones are the traditional method of the open circles. And if you look at, you can't really see it here because everything's plotted over on top of each other, but if you look from a top view, you see that we've dramatically condensed our events together So we have much more accurate relative locations compared to what we had before, because basically we have about a half a millimeter uncertainty on our locations with the traditional method of calculating the location, but our sample is only a couple millimeters wide. So you might be able to put it in the right quadrant, but here you can see now you can get some pretty accurate relative locations. And you just see at the bottom, it's showing that the event separation has dramatically decreased for the red and the blue compared to the gray. So that's good. We can have some more accurate locations, but from the double difference method, we only get relative locations. We don't know where they are in space. We know their orientation, and we know where they are relative to one another. But in absolute space, you could move this event cloud around and put it anywhere. So, well, where do you put it? Why did I put it there? Because the other thing we can do is we can take our recovered sample and we can run a CT scan on it. And when we CT scanned it, and we section out there, so we see this big fault in the sample, and we can section out that, which was done by Dave Eady at the University of Texas at Austin. So thanks for that, Dave. But basically, you see that it has these two kind of like arms to it, and we had these two groups of events. So basically, these two events came from these two sides of this kind of conically looking fault here. So we can actually link related events down to the subfault level when we use this type of analysis, this double difference type of analysis. And this is just a little movie because movies are kind of cool. So here's the fault in gray, and then we're seeing our events pop up. Now they're color coded instead of time, instead of cluster. But you can see that they're kind of, you have one side of the fault was one cluster, and then the other side is the other. And for this one, they're kind of, they're sort of random in terms of where they show up in time. With this one, eventually you'll see it is starting to migrate towards this direction. But yeah, I didn't realize it was this long. But anyways, you get the picture. So we can actually relate specific events and how they, so the idea here is that basically you have a bunch of events in the same direction from the same process, and over time, they generate a weak plane that can lead to macroscopic fracture. So we can also look at the focal mechanisms of our events. And this is important because, so the focal mechanisms will tell you the orientation that a fracture happens and the type of fracture. Did it open up like those tensile cracks I talked before? Was it shear fracture, like slip on a fault? You know, what happened? Did it just explode? Did it implode? And these focal mechanisms will tell us something about that. And I should mention that deep focus earthquakes, if they are created by phase transformations, they're not just as simple as a decrease in volume from the phase transformation leads to an implosion in the earth. Because when we look at their focal mechanisms, we see that they're always shear fractures or shear earthquakes, the same way you have with shallow earthquakes. So something has to be happening when we change for the phase transition to lead to shear failure. So the way seismologists look at these focal mechanisms is in terms of these beach ball things. So if you look at this plane 2 thing here, don't worry about plane 1. Along this plane, you have slip, shear. So if you're in this quadrant, so this is what the rock is actually doing when it fractures. It builds up stress and it goes like this. If you're in this quadrant, if the fracture plane's here or the earthquake plane's here, it pushed towards you. If you're in this quadrant here, it moved away from you. So the rock dilates. Here it compresses. Now, if you're over here on the other side of the fault, well, now if you're in this quadrant, it was a compression towards you. But if you're in this quadrant, it was a dilation. And then they generally plot these things in terms of these beach balls, where you have the dark regions are all compression and the white regions are all dilation. Oops. And this is just showing a bunch of focal mechanisms. So the way we calculate these is you look at the first motion, or the first little wiggle in your seismogram. So you can imagine the wiggles that you measure at your seismogram, the first wiggles are a reflection of how the rock moved where it actually occurred. So if you look at, imagine if you look at this transducer, this fracture moved towards this transducer, but it moved away from all these ones. It also moved toward this one. So if you look at the direction that it moved and how much, namely the amplitude, then you can do an inversion to get back to how did this thing fracture? Did it open? Did it shear? Did it explode? Etc. And the orientation, the geometry of how this occurred. So usually they will break these focal mechanisms things down in terms of what's called a moment tensor decomposition, but you have an isotropic component. So it's either an explosion or an implosion. And that would just be like a bomb or something. You have a double couple, which is the shear component of it. So that would be like an earthquake. You have shear slip on a fault. So basically all earthquakes are this thing here. And then you have this more abstract thing called a compensated linear vector dipole. So I'll refer to it as CLVD because that's a bit of a mouthful. But this is basically where you have motion in the vertical direction, moving, compressing, and then you have radial motion outwards. But the thing is, so this thing kind of seems like our experiments, but in this case, it doesn't, nothing actually opens for a pure CLVD component. It would just change shape. But the reason they do this is that if you take these three components with different percentages of them, you can make any type of fracture. So you can find out what type of fracture it was. So for here, this is just, this particular one has 2% isotropic component, 30% double couple, and 67% CLVD. So the way these are often plotted are on this thing called a Hudson TK plot. So if you have a shear fracture, that's right in the center of this plot is where it's going to show up. All the shear fractures just show up right in the center. Now you have the isotropic component along this axis. So you have explosion going up, implosion going down. So if it was a pure explosion implosion, it would be on this line. And then you have your CLVD components along this horizontal line here. But then of course they can have different amounts of these different components. So it could show up sort of anywhere around here. So now if we look at our data, basically it falls right along this line. So we have a bunch of double couples at the center, which are piled up on top of one another, but we also see a significant amount of CLVD components, and I'll explain why that's the case in a moment. So here's just sort of the density plane. You can't even see, there's so many that are piling up in here that you can't even see through the dots to see the like red part of the heat map. So we have mostly double couples, but or shear fractures, but we also have a significant part of these CLVD components along the sides here. And if you look at this here, each one of these is just a bar graph. So we basically, the important part is we don't have any isotropic components, any explosions or implosions. And this is significant because at low pressure, in order to generate fracture, you first need to open cracks. So that would be, so tensile cracks fall right on this line here, but we don't see any tensile cracks. You always do at low pressure. That's how things break, is first you open cracks, then they link up. but because we're under pressure, we can't open cracks. So we have mostly shear. I think all shear, and I'll say in a minute. But if you look at this plot on the right, this is just basically showing you about 2/3 of it is pure double couple, and then you have some of this CLVD component. But the CLVD thing, it's basically just, these are the error ellipses for the data I was showing. We have very good resolution of whether or not it would be an explosion or an implosion, but we have very poor resolution in terms of the CLVD components, because depending on the orientation of a shear fracture with respect to where the transducers are in space, it can become it can become impossible to distinguish between this situation and this situation, which is why we have large CLVD components, but it's also why they have such large uncertainties. So I'm alleging that we have entirely shear fractures in our experiments, which is completely different to low pressure brittle failure. The other way this may play a factor, the other way you can get CLVDs is if you have a double or a shear fracture on a curved surface. And we do see shear fractures on curved surfaces. So this is like a ring fault here. And you can also have, if you have two conjugated faults, so two conjugated shear faults that happen simultaneously, that can sort of masquerade as CLVD. So this probably plays some role in it, but most of it is just our uncertainty in trying to determine exactly sort of what the focal mechanism is. But if we compare this to low pressure brittle failure, or actually, so this actually happened at high pressure, but we were degassing, so you'd expect some explosive component. Most of this was related to stress transfer, so you actually see a lot of shear fractures, but it also had an explosive component, which we can measure. So if we had isotropic components, we would measure them. And this is just an experiment that, somebody I forgot to reference by accident, ran. And they ran it at 75 MPa, and they generated tons and tons, like thousands of fractures. But you notice their isotropic component, so their explosion implosion component, is getting up to 30%, 40%. They have very significant components. So they would have a lot of stuff in this area, and we don't have any. So this really is a different style of fracture. We're generating a phase transformation, and we're getting slip along these weak areas where the phase transformation occurs, probably because of grain size reduction. But these are tiny samples in our lab. Like, what does this have to do with earthquakes? Earthquakes are huge. Do these tiny samples, do they actually have anything? Can we relate them to natural seismicity? And more broadly, earthquakes, are they scale invariant? So it's kind of like saying, is a big earthquake just a small earthquake but bigger? Is it the same physics in a big earthquake that you have in a small earthquake? And that's kind of another way of saying, is it a self-similar phenomenon? Is it fractal all the way down, where you just have the same process happening on a smaller scale? Or is there different physics between small earthquakes and large earthquakes? And this is a broad question in earthquake seismology, not just deep focus earthquakes. So one way that they try and test this is through something called stress drop. So imagine you're building up stress on a fault, and then you release it. You have more stress here than after you release it. So the change in shear stress before and after a fault is what you call a stress drop. And so if you look at this plot on this side here, so you have seismic moment getting larger to the right, and then the size of the physical size of the earthquake getting larger here. So the big ones are down here, small ones are up here. And then you have these lines of constant stress drop. This is a log plot, by the way. So it appears that earthquakes are independent of, it appears that stress drop is independent of earthquake size. So a large scale earthquake, the change of stress on that fault is the same as a little tiny one in an acoustic emission stick slip experiment, because it's following the same stress drop pattern all the way down. Well, how do ours compare? Well, I think people probably know this, but if you don't, so in the time domain, you have a bunch of wiggly lines. These are your harmonic motion for your shaking, but then they add up to make some complicated function that you can see down here at the bottom. So these are a bunch of different frequencies that are adding together to make this more complicated squiggly line. But then when you do something called a Fourier transform, you can separate out the frequencies that are involved in your time series, or the oscillations you have in time. You can find out what frequencies are within that signal. So then you'd be working in you can switch back and forth between the time domain and the frequency domain. And if you look at the frequency domain for just regular earthquakes, a sort of earthquake spectra looks, their frequency spectrum looks something like this. Big events, they have high, so this is seismic moment here, so the magnitude of the earthquake. And what you have is you have a saturation at low frequencies. This is also a log-log plot, by the way. You have a saturation at low frequencies until you reach this corner frequency thing, and then it starts to fall off as a straight line on this log-log plot. And as you go smaller and smaller in magnitude, you saturate out to higher frequencies. So you have higher frequency components in the smaller events, which kind of makes sense because they're oscillating on a smaller scale. So basically the question is, does this pattern here work all the way down to little tiny events? So the way you would do this is, if you can measure the corner frequency, which is related to the size of the earthquake. If you can measure the corner frequency, you can estimate the size. And then if you can measure the magnitude, you can estimate the stress drop. So basically, and if you don't understand all this, don't worry too much about it. The conclusion will make sense. But basically, in our case, it's very difficult for us to make this spectrum because we have a transmitting medium, we have a sensor response. But what you could do is that if you divide the frequency spectra, you can remove all that. So what we do is we take sort of a big event and a small event, and we divide the two. And what you'll get is that at the beginning, before you hit the corner frequency of the big event, you get a constant because they're both just flat. Then you hit the corner frequency of the big event, it starts to go downwards until you reach the corner frequency of the small event, and then you get another constant. So you should get some plot that looks like this. Now, in order to do this, you have to be able to capture the whole frequency spectrum. So you can't just capture a little piece of it. You have to be able to get the entire frequencies that are included within your acoustic events. And the way we do that is we basically just, no single piezoelectric transducer will be able to cover the whole range. So instead we use transducers with different resonant frequencies, so different frequency responses. So you can sort of see channel 1 and 3, we have 2 megahertz resonant frequency, 2 and 4, 5 megahertz resonant frequency, and then 5 and 6, 15 megahertz resonant frequency. And of course, these have bands. So between these 3 types of transducers, now we can cover the whole frequency range. And then of course, in order to get acoustic events, you have to run an experiment. So this is the same data before. We broke a piece of Mg2 GeO4 under high pressure, so we have acoustic events. So this is just showing some frequency spectra. So here's the acoustic signals. Here's the Fourier transform of them, so the acoustic signals. And you see that the higher frequency transducers pick up higher frequencies, not too shocking. And then if you take the log-log of this, you get something that looks like this. So now we can make our frequency spectrum by taking portions of each of these and sort of stitching them together to get an actual frequency response. And then we divide them out and we get these sort of ski hill looking plots we had before. So this is a large divided by a small event. So we go up to the corner frequency of the large event. So we get that. And then it falls off until it turns over and we can get the corner frequency of the small event. Now, for a large versus medium event, this is the same large event. We measure roughly the same corner frequency, so that's good. And then the medium event, it should have a lower corner frequency than a really small one, and indeed it does. So it seems like this is working. So once we have the corner frequencies, we can estimate the source radius. If we want to get the stress drop, we also have to measure we also need to know the magnitudes. This is actually pretty difficult because you have an acoustic little earthquake that happens here, and then it has to travel through a medium, and then you measure it at your sensor. So the actual size of the event that created that, it's kind of difficult to know. So basically, I came up with a calibration based on looking at, because you can estimate the magnitude from the focal mechanisms or the moment tensor. So basically, we took 2 megahertz transducers, we found out what their magnitudes were and put in some correction factors, and then we get this kind of scaling law here. You don't necessarily need to know all the details into it, but this is probably our biggest source of error. It's difficult to know for sure what the magnitudes are. I'm actually pretty happy with the corner frequencies. So then we get, here's the result. So here's our like corner frequency stuff, which is related to the radius and seismic moment. So we're down at a magnitude kind of -9 to -10, whereas a regular earthquake might be like 7. So that's 16 orders of magnitude or something. But if you look at the radii, they're around sort of a millimeter up to hundreds of microns. That makes sense. That's about the sample size. But you notice too, if you look at these lines of constant stress drop, our events have as independent, the stress drop is independent of size. So what this is saying is that it scales with itself. So that's good. Okay, they scale with themselves. But how do they compare to real seismicity? And basically, they scale very well with that too, which I find pretty astonishing because one, this is over 25 orders of magnitude, and we have the same change in shear stress on our 100 micron cracks that you have in a magnitude 7 earthquake, which is kind of crazy. But what's really crazy about it is that they're not regular cracks. They're generated by slip on a band of high pressure phase. So the fact that they scale well with large scale earthquakes, as well as induced seismicity and underground fractures and other things, I find pretty remarkable. This is just saying we also perform the same type of analysis. Instead of using Mg2-GeO4, we use Mn2-GeO4, which transforms from olivine to Wadsleyite. This was led by a former postdoc at Jesse Cars named Feng Shi, who's now at the China University of Geosciences in Wuhan. And basically you get the same thing. You have a narrow temperature window in the high pressure stability field where fracture occurs. It doesn't occur in the olivine stability field. You get another plot that looks like this. And then you can see these little dots here are the high pressure phase dotting. So these are where you can have slip within these bands. Basically, olivine to Wadsleyite in this material behaves identically to olivine to ringwoodite in Mg2-GeO4. And since this is force, I should mention that we also have run these experiments with big samples. Big samples are the key for this. You can generate larger fractures. You generate much more events. Here we got about 3 times as many, but we didn't strain it as much as we did in the previous examples. And also our transducers are much further away in this case because we have a double stage anvil system. Didn't show a diagram, but I suspect for this type of sample, which is 12 millimeters by 6, I actually have one of these, and this one you can sort of see. Yeah, so we get, I would estimate probably a factor of 10 times the amount of acoustic activity. And then this is just a CT scan showing going through. We can also change the aspect ratio. So before, what we have stress concentrations near the top, which tend to generate fracture, but now we can move the fractures away to have them happen near the center of the sample. And that's related to it being long and thin compared to short and fat, which we had in our previous examples. So how long have I been talking for? Probably a long time.
We're at 12:53 right now.
Good, because I am done. So to conclude, basically, we are able to generate the high pressure phase. To generate fracture, we can see it within to the subfault scale, which is on the hundreds of microns. The focal mechanisms are all shear fractures, the same as deep focus earthquakes, and they appear to scale with deep focus earthquakes and other seismicity. And I didn't have time to talk about it, but here's what happens when you break something under 8 GPa. So this is some silicate data, which I left out of this talk, but I will take any questions.
All right, thank you, Tim. In the chat, Luciana says, thank you for showing us these really interesting experiments. I agree. These are really cool. I'm not familiar with a lot of this, and I feel like you explained it really well.
I did, but yeah.
Okay, if anyone has any questions, you can feel free to type them in the chat and I'll read them here, or you can raise your hand. Ben, you can go ahead and unmute yourself.
Oh, hi, Tim. So
Hi,
it's
Ben.
very interesting talk. Yeah, about this, like the last figure that you showed. So have you get a chance to do any TEM on the on the sample that you have with this high pressure like a band here?
Like the one that we're looking at?
Yeah.
Yeah.
So what?
I'm glad you asked that, because you can see there's like tons of slides I cut out because I knew I wasn't going to have time. So I didn't talk about the silicate data. But in terms of TEM, if you look at the grain orientation, we didn't get very good bright field TEM to like see the high pressure phases. But one thing that we see are kink bands. So if you if you look at that picture before, you see how there's something geometric about how it fractures. All of these things are at a different orientation. So if you look at, we see these long, thin bands where the high pressure phase forms. So you see how there's like a band here, and then there's another band that has a bunch of cracks in it that are all in the same direction. Then there's another band, and there's another band with cracks. All of these things are at a different orientation. So these little cracks don't happen under high pressure. They're when we unload the sample. And I think it has to do with the anisotropic, because olivine's not isotropic. But if you look at the orientations across these things, so here's the original picture. Oops. And then you move across it, you see that you're flipping orientation. So at the beginning, we're at like 80. These are just relative. Then it goes to 0 and back up to 80 and to 0. But if you're looking for like a nice TEM image of grain size, I don't really have one. Sorry. Which is, I think, what you did want to see.
Thank you.
I should say, though, Ben, that the grain size almost certainly has to be small, because the bands that we see are at very most 100 nanometers wide.
Okay. Yeah, that's good to know.
Yeah.
Nathan, you can go ahead and unmute yourself.
Hi, can you hear me? Hello?
Hello?
Oh, you're very quiet.
Sorry. Really interesting talk. You might have explained this already, but I had to refresh my Zoom a couple of times. So we have these second phases forming, right? And then we're having slip along that second phase.
Correct.
So how can you tell that the second phase is not a result of the slip, rather than that's like the surface slip? Does that make sense?
That does make sense. In some sense, you can't necessarily know for sure, but the reason I think it is if you look, so like if you look at this plot here, when we're deforming it at low temperature, so the olivine's metastable, we don't generate the high pressure phase, we don't see any acoustic emissions. So it seems reasonable to believe that once we generate the high pressure phase and start seeing acoustic activity, that it's probably from the phase transformation, not from like slip that occurs and then the phase transformation just happens in that place. Does that make sense?
Yes, that does. Thank you.
In the chat, Pam Burnley asks, do you see significant offsets parallel to the kink band boundaries?
Do you mean like, so the answer is no, not really. But part of that is, like where I've seen the most of this is in my silicate. So this is an iron-rich silicate. So it's the molar ratio is 75 to 25% iron to magnesium. But it's the only phase that's in there, at least in the starting material. We grow high pressure phases, but if you have a single phase, you can't really see slip, if that makes sense. Like you need to see something that has slipped. Whereas if you just see, how do you know it wasn't there in the first place? I don't know if that answers your question, Pam. So the answer is no, I don't, but it might be there.
She asks, what about offset on the grain boundary where the kink band intersects?
Offset on the grain boundary. No, not necessarily. No, we don't. We actually, here, I'll show you some EBSD images of some kink bands. So here's in all three of the materials, the Mg2, GeO4, and then the silicate. And you can see that the kink bands are within individual grains.
She says, okay, I don't see that either, but kink bands are nice places for spinel to nucleate.
They are. I think I have an image of that too. So here, this is Mg2GO4, Mn2, and then the olivine. And you can see that at these bands, you can see there's a kind of lighter phase. So you have a lot of stress buildup at the at the interfaces of these bands, which provide nucleation sites for the ringwoodite or wadsleyite.
Thanks everybody for your great questions. And thank you to Tim for giving us this great talk.
Thanks for inviting me.
We'll see you all in 2 weeks back here, same time.